But the next topic is this is the last topic in second unit this is about implementation models. Here what is meant by the here implementation models means here in this data will be represented by a pair of consisting of a descriptor and a data object. Here in this descriptors contain the most relevant attributes. We are having some of the attributes these are attributes we are needed to the during the translation process. During the translation process here in these descriptors are kept in a symbol. It must be for during translation, and only a subset of the attributes store these attributes to be saved at runtime here. Here these attributes, this data will be appropriate by some specific purposes. We are using the data here. Here in this data we are using the descriptor and data object. Here in this data descriptors are kept in a symbol table, during the translation, and only a subset of the attributes is stored there needs to be saved at the runtime here. Here in this we will pay here little attention to the physical layout of these descriptors, which depend on the overall organization of the symbol table. Here in this symbol table we are having some of the attributes, some of the data types. These are the stored in the symbol table. Here next point is next one is in this implementation models. First one is built-in and enumerations. Here this is the built-in and enumerations here. In this built-in and enumerations means, built-in means we are having data types. Built-in is the data types, and enum, this is one of the data type here. Built-in data type means already we predefined that type is called a built-in data types. Here in this built-in data types, here integer and reals are the hardware supported for the most convenient computers here. Here in this provide fixed and floating point arithmetic here. Here integers and reals which are provided for the fixed and floating point arithmetic here. Here in this built-in we are having existing computers may also provide different lengths for the supported arithmetic types. Here. These are the existing computers may also provide the different lengths for the supported arithmetic types here. Here if the language provides the different lengths for the arithmetic types, and here this language here contains the hardware, means here it is implementation free to the ignore the prefixes here. For example, in a language like C here, by long and short prefixes here. Here in C language we are having by long and short prefixes. Here if the language provides different lengths for arithmetic types. Hello? If a language provides different lengths for the arithmetic types, and these are the hardware, it does not implementation is usually free to the given the prefixes here. Here in case of C language, it is reflected by the long and short prefixes. Here if the language provides the different lengths for the arithmetic types, and this hardware does not implementation by we use to ignore these prefixes, here in this case of C language, it is only required that short should not be a longer, and then int should not be a longer than int, which should not be longer than long, Here, if this we ignore this issue of different lengths for arithmetic types here. If we ignore this issue of different lengths for the arithmetic types here, for simplicity, integer and real variables may be represented as variables. Here, if we ignore the issue of the different lengths of the arithmetic types, for simplicity, integer and real variables may be represented as the values of the enum type, enumeration type. Here, this enum type can be mapped one to one, and to the integer values in the range of 0 to n minus 1. Here, for this cardinality of enum, this mapping does not introduce any possibility of the mixing up of values by enum. Here, in this enum is enumeration data type. Already in enumeration data type, already we learned in C language here in enum data type. Here in this built-in means we have integers and reals. These are the hardware supported on conventional computers, which provide the fixed and floating point arithmetic here. Here, these are the existing computers may also provide the different lengths for the supported arithmetic types. Here, if this language provides the different lengths for the arithmetic types, and this hardware does not an implementation, but usually here we ignore the prefixes. Here. In the case of C language, it is only required that short should not be longer than int here. In case of C language, it only required that short should not be longer than int. Here we should not be longer than long here. Here, if we ignore this issue of different lengths for arithmetic types, for simplicity, integer and real variables may be represented as like this. Values of the enum data type. Now, this is the representation of integer variable. This is the figure representation of integer variable. Here, integer descriptor means in this implementation models, we implement data, and data can be represented by descriptor and object. Descriptor and data object here. This is the descriptor here. This is the data, integer data. Next, sign bit. Here, this is the memory word. We have to represent an integer variable like this. This is the floating point variable. This is the descriptor, and this is the object. We represent this descriptor like real here. This is the sign bit for here. For this floating point variables, we are having mantissa part and exponent part. These are the two types of data. This is the memory mode here. Here in this can be mapped to 1 to 1 and to the integer values in the range 0 to n minus 1. Here. This is the figure representation of integer variables. This is the representation of floating point variable. Here we take this is the descriptor, this is the object here. Data can be represented as the descriptor and object. Here. Next, this is the descriptor. In this descriptor, we are having integer. Next, this object contains the sign bit here. You have to represent this is the integer variable, and this is the representation of floating point variable. For this floating point variable, here descriptor can be represented here real. Next, this is the in this for real we are having sign bit for mantissa, sign bit for exponent. sign bit for mantissa and sign bit for exponent. Here k bit exponent and h bit mantissa. This is the memory word. This is the memory word. Next here for the this here for this we have some of the issues of different lengths of the arithmetic types. That's why we have to ignore that. That's why we are using the integer and real variables. Integer and real variables. Real variables values of the here enum data type. Here enum means one of the data type here. Next enum can be mapped 1 to 1 to integer variables in the range 0 to n minus 1. Here n being the cardinality of enum here. N being the cardinality of enum here. Here this mapping does not introduce any possibility of mixing up these values of type enum. Here this mapping does not introduce any possibility of mixing up values of type enum. Here enum with values of any other enumeration type, if all run access or via descriptor containing the type information. Descriptor containing the type information. Here the use of the descriptor, it is not necessary for the typed languages. The use of the descriptor is not necessary for the typed languages. Here what is the another point means, in a language like C, the mapping of enumeration types to integers is not a just part of the implementation of type Here this here in this descriptor, it is not necessary for the typed languages. It is not necessary for typed languages. Here it is not necessary typed languages means here these are accepted by the through descriptor only. That's why it is not necessary for typed language. What are the typed languages? C, C++, Java. These are the typed languages. Here note that in a language like C, the mapping of enumeration types of integers is not just part of the implementation of the type time. Here in this booleans and characters can be viewed as enumeration types and implementation as above. To save space here booleans and characters can be viewed as enumeration types and it is implemented as below means here to save space, characters and booleans can be stored in storage units. Here in this booleans and characters can be viewed as the enumeration types. Here it is implemented like this to take this advantage of the language here. Here in this implementation we are having the programmer to take the advantage of this knowledge here. Here in this to break this to type of the access implementation directly here. Here in this booleans and characters can be viewed as the enumeration types and this implementation like this. Here in this to save space and characters and booleans can be stored in storage units, smaller units than word. Here for example bits are bytes here. Here booleans and characters can be viewed as enumeration types and it is implemented like this. Here to save space, characters and booleans can be stored in the storage units and smaller than a word here. Here for example bits are bytes. Here in this addressable in a hardware, here it can be retrieved the suitable word manipulation instructions. Here in this in such a case, here individual characters of the booleans may be the less efficient, and it would save the memory space. It would save the memory space here. Here this choice of implementation model, it depends on the trade-off between the speed and space. Trade-off between the speed and space here. Here next topic is the here structure types. Next topic is the here structure types. This is the next topic ma. Here structure types means, here why we are using this structure types means, here program types will not depend upon the specific syntax. Here program types will not be depend on the specific syntax. It is adopted by an existing language. It is adapted by an existing language here. It will refer to the hypothetical, next it self-explaining and programming notation here. Here in these programming types will not be dependent on the specific syntax. It is adopted by an existing language here. It is adopted by an existing language here. It will refer to an hypothetical self-explaining programming notation. Here next in this, for example, we take here x float array 0 to 10. Here we take x variable float array means, here this means the declaration of say a finite mapping of x here. Here x tends to float array of 0 to 10. Float array of 0 to 10 here. Here it is the shorthand for the declaration of a type followed by a declaration of an array variable. It is a shorthand for a declaration of a type followed by a declaration of an array variable. Now this is the next this is the type. We give the type here. Type x type is float array 0 to 10 x type. Here type x type is float array 0 to 10 x type here. Here we assume that if a type declaration, it contains the structured component. Here we assume that if a type declaration contains a structured component, such component is separately defined by a type declaration. Such component is separately defined by a type declaration. Here for example, if a field of a Cartesian product is a finite mapping. Here we assume that if a type declaration contains a structured component, here such component is separately defined by a type declaration. Here for example, if a field of a Cartesian product is type finite mapping, here there are two type declarations here. First declaration, the declaration of an array type T, and the declaration of structure with a field of type T. Here there are two type declarations. Here first declaration is of an array type T. If there are two types of declarations here, the declaration of an array type T and the declaration of a structure with a field of type T. Here in this consequence, each component of a structure type is either built-in type or user-defined data type. Here for these assumptions, here each component of a declaration or each component of a structure type is either a built-in type or it user-defined type. Here for this built-in types, here each variable is described by a descriptor here. For built-in types, for each variable is described by a descriptor and its storage. Here the descriptor contains a description of the variable's type. Here the descriptor contains a description of the variables type. Here in an actual implementation for efficiency reasons, all variables of a given type, here in this simplified descriptor, it points to be separately stored descriptor for that type, that is here we are using the structured types. First topic is the Cartesian product. Here in this Cartesian product, the standard representation of a data object of a certain Cartesian product type, it is a sequential layout of components. Here the standard representation of a data object of a Cartesian product type is a sequential layout of components. Here for example, this is the syntax type another type y is struct. Y is struct means float a into b. Here type another type y is struct. Type y is struct here. Here float a into b. Here type sample type means here these are having two types. We are having two types here. Another type sample type here. Here type another type y is struct. Float a into b. Here type sample type is struct. Int x. Here another type y. Here this is the sequential layout of components. Here sample type x. We close the sample type x. X is closed here. Here each component of the Cartesian product, it occupies a accessible means addressable storage here. Here each component of the Cartesian product occupies a certain number of addressable storage here. Here for this Cartesian product, the standard representation of a data object of a Cartesian product type is a sequential layout of components here. Here in this type another type y is struct here, float a into b. Here type sample type is struct int x, another type y, sample type x. Here each component of the Cartesian product, it occupies a certain number of addressable storage. Next, this is the representation of the Cartesian product This is the representation of the Cartesian product. Here the before I explain here in this slide, Cartesian product means it is a standard representation of the data object of a Cartesian product type. It is a sequential layout of components. Here sample type another type. Here we take the sample type. Here struct constructor, you have to use the selector x, type int, reference means we give the address integer value, selector y, floating point value. Next type, we take the another type here, struct a. Next selector, we take the selector capital A, type float, we give the reference means you give the address for that. Address for another type is floating point value. And next one is next we take the selector b, type int, we give the reference to the integer value. This is the representation of the Cartesian product. Next, this is the next sample type, and we take the another type. Here the constructor is struct. In this selector, we take the selector is x, type is int, we give the reference is integer value, and selector is y, and type. Next we go for the another type. This is the reference for y, we give the reference is in floating point number. Next, Next one is the finite mapping. Here in this finite mapping, next topic is the finite mapping ma. Here in this finite mapping, here conventional representation of a finite mapping allocates a certain number of storage units. A conventional representation of a finite mapping, it allocates a certain number of storage units. Example, words for each component. Words for each component. Here a conventional representation of a finite mapping, it allocates a certain number of storage units, that is called here example. Example, we take the words for each component. Example, for each component words. Here for example, we take type X and type X, and type is float array 0 to 10, means 0 to 10, means here X type T, X type T, X type X, X type X here. Here in this finite mapping, it is a conventional representation of a finite mapping allocates a certain number of storage units. Certain number of storage units. Example, words for each component. Example, for each component. Here example, we take here type X, type is float array 0 to 10. Type X, type is float array 0 to 10. X tends to type X, X tends to type X here. Here a reference to X of 1. Take here X of 1. It is computed as an offset from the address. Offset from the address. Here a reference to x1 is computed as an offset from the address. Offset from the address. A tends to x of the first location of array. First location of array. Here this a reference to x1 is computed as an offset from the address ax of the first location of the array. First location of the array. Here next. This is the representation of the finite mapping ma. This is the representation of the finite mapping. Here x type. Here we give the x type, means we give the type, and constructor is array. Here we give the constructor is array here. Type x type, constructor array. We take the index type is int. Take the index type is int. Lower bound 0, upper bound 10. Lower bound 0, upper bound 10. Here range type float. Here range type float. We give the reference to the data object. We give the reference to the data object 0 to 10. 0 to 10 here. Here we give the type x type, constructor array. We take the constructor array, index type int, lower bound is 0, upper bound is 10. Upper bound is 10, and range type is float. And range type is float here. Here we give the reference to the, here we give reference to this data object, means 0 to 10. 0 to 10. This is the, here x of 1 is computed to the offset from the address a of x. A of x of the array. A of x of the array. This is about the representation of the finite mapping. Next one is the, next topic is the union and discriminated union. Union and discriminated union here. Here these are the union types, do not require any special new treatment to be represented here. Union types do not require any special new treatment to be represented here. Here a variable of a union type as a descriptor, that is a sequence of descriptor, that is a sequence of descriptors here. Here in this, here union types do not require any special new treatment to be represented here. A variable of a union type has a descriptor, that is sequence of a descriptor. Here these are the, here this, in this union type we are having the union, it is a descriptor, that is sequence of descriptors of the component types. Here the instance of the values of the component types, you have to share the same storage value. How to share the same storage value. And for this same storage value, for example, we take the type X, type is float array 0 to 10. Here type X, type is float array 0 to 10. Type Z, type equal to record. Type Z, type equal to record. Here you have to give the case is, in case we take the boolean of true. Take the boolean type is we are having true or false. Take the boolean of true means integer. Next boolean of false means b of x type. Here in this union types do not require any special new treatment to be represented here. Here a variable of a union type as a descriptor that has to be represented. Here a variable of a union as a descriptor, that is sequence of the descriptors here. Here of the component types. Here instance of the values of the component types have to share the same storage value. How to share the same storage value. Here for example we take the type X, type is float. Here type X, type is float array 0 to 10. Here type Z, we take the type X, type is float array 0 to 10 means type Z, type equal record. And case kind. Here case kind we take the boolean of true in integer. For a integer we are taking two values here, a and b. A integer and b is the false, otherwise take the false. X type we have end here. This is the example for the union here. Next, this is the representation of the discriminated union discriminated union here. Here in this discriminated union here, in this type constructor, selector, type, reference, case table, these are the fields these are the attributes of this Z type, X type, these are the two here. In this Z type we have to take Z type here. Constructor is variant record here. Constructor is variant record. You have to select the kind. Here. Type is boolean. You have to type is boolean here. Reference we take the boolean value. Here case table. In case table we have true or false. Case table is true, false. Take the true here. True we go for the b. Int. Next, here false. In the case Z type is false, here we go for the A selector type. Here. Here in this Z type here, variant record, constructor is variant record. Next kind, what kind of? Next selector, next type we take type boolean. Next reference means we give the address. We give the reference is boolean. Reference go for the boolean value. Here the case value means we take the true. In case table we are having true, false. This is the case table here. In case table we take true. In this the condition is true means we take boolean is take true. It's go for the b int means give the selector, type and reference. Is next it is the condition means we take the boolean value is false. We go for the a selector a. Here type X type, constructor array, index type int. Next lower bound is 0, upper bound is 10. Range type is float. This is the reference. This is the representation of the discriminated union. Next, next topic is the power set. Here these power sets can be implemented efficiently. In terms of access time. Here in this power set A power sets, it can be implemented efficiently in terms of the access time and manipulation time and storage space. Here this power sets, it can be implemented efficiently in terms of access time, manipulation time and storage space, and it is provided that machine at least has many bits as per potential members of the set, means that is the cardinality of the base type. Here power sets can be implemented efficiently in terms of the, what are the terms here? Access time, manipulation time and storage space. It is provided that a machine word, means this word it at least has many bits as there are potential members of the set here. That is the cardinality of this base type. Here the presence of the ith element, in a certain set S is denoted by 1. It is denoted by 1, and as the value of the ith bit of the word is associated with the S. Here. The presence of the ith element of the base type in a certain set S. Is denoted by 1. S is denoted by 1 as the value of the ith bit of the word, it is associated with S. Here the empty set is represented by all zeros in the word. Here the empty set is represented by all zeros in the word. Here the union between sets, it is easily performed by an OR. Here in this power sets we are having union between sets, it is easily performed by an OR between the two associated words, and it is an intersection by an AND. Here if the machine does not allow bit level access, it is test for membership. It requires shifting the required bit into an accessible word position. Means example, the sign bit or using a mask. If a machine does not allow bit level access, test for membership requires shifting the required bit here into an accessible word position, example the sign bit here, or using a mask. Here the existence of such an representation of this power sets here, it is responsible for the implementation defined limits for the cardinality of representable sets. It is normally equal to the size of the memory word. Here the existence of such an Peel representation for power sets, it is responsible for the implementation defined limits for the cardinality of representable sets here. It is normally equal to the size of the memory word. This is about the power sets. It is implemented efficiently. In which terms it is efficiently means access time, manipulation time and storage space. It is provided that a machine word has at least many bits as there are potential members of the set in the presence of the ith element of the base type in a certain set S. It is denoted by 1 as the value of the ith bit of the word here. The empty set is denoted by zeros in the word. Next one is the sequences. Next topic is the, see, these are the implementation models ma. These are the first built-in and enumerations. Next one is, what is the next one? First one is built-in and enum. First implementation model. Second implementation model is, what is second implementation model? What is second implementation model? Next one is the sequences. In this sequence of elements of arbitrary length on secondary storage. Here in this sequence of elements of arbitrary length on a secondary storage, it is represented as files. It is represented as files here. Here file management is ignored here, being out of scope. Here file management is ignored here, being out of scope here. Here in this file management, strings are supported by many languages. Strings are supported by many languages. Here are just array of characters. Just array of characters here. Here in other languages such as Snowball 4 and Algol 68. Here in other languages such as Snowball 4 and Algol 68. In this languages, strings may vary arbitrary in length. Strings may vary arbitrary in length here. In this languages, we have no programmer. It is specified upper bound. It is specified upper bound here. Here, this kind of array with a dynamically changing size. This kind of array with dynamically changing size must be allocated in the heap here. Here in these sequences, sequence of elements, it has the arbitrary length on a secondary storage. It is represented as files here. In this file management, it is ignored here, being out of scope here. Here in these sequences, strings as supported above many languages are just array of characters. Here in the other languages such as Snowball 4 and Algol 68, strings may vary arbitrarily in length. Here having no programmer specified upper bound. Having no programmer specified upper bound here. Here this kind of array with dynamically changing size must be allocated on the heap. Next. Our next one is the classes. Next one is classes topic. First, in this classes topics, user defined types specified by the simple case. Here in this classes, user defined types specified via the simple class construct are easy to represent as extensions of the structures. Here in these differences are means class. What is meant by class? The group of objects is a class here. Group of objects is called a class here. Here in this user defined types, it is via the simple class construct are easy to represent as the extension of the structures. Here. Here in this classes, what are the differences means? Only public fields are visible outside the construct. Only public fields are visible outside the construct, and such fields must be tagged as public in the descriptor. Such fields must be tagged as public in the descriptor. Here some fields may be routines. Here it is necessary to be able to store routine signatures in descriptors. Here some fields may be routines. It is necessary to be able to store routine signatures in descriptors. Here in these classes, user defined types, it is specified via the simple class construct. Here it is easy to represent as extension of the structures here. Here in these are the differences only the public fields are visible outside the construct. Here such fields must be tagged as public in the descriptor. Here some fields may be routines here. It is too necessary able to store routine signatures in descriptors. Next topic is the pointers and garbage collection. Here. Here what is a pointer? It holds as a value the address of an object. object of the type. Here to which the pointer it is bound to be the some special null value. Here pointers usually can have a special null value. For example, we are using in C and C++, we are using a void. We are using here void. In Pascal we are using nil. Here such a null value can be represented by an address value. It would cause a hardware, it is generated error here to catch the an advertent reference. It is a pointer with null value here. Here pointers usually can have the special null value here. Here null value means void. We are using void using in C and C++. In Pascal we are using null here. Here this is the null value, it can be represented by an address value. It would cause a hardware generated error here. In this to catch and this advertent reference by a pointer with null value here. Next another point is in this pointer variables are allocated as any other variable on the activation record stack. Here activation record stack. Here in this memory, in this data objects that are allocated by the runtime allocation, primitive new are allocated in the heap here. Here next point is the in this pointer variables are allocated as any other variables on the activation record stack. Activation record stack here. Here in this activation record stack, data objects that are allocated by the runtime allocation, primitive new are allocated in the heap here. Here in this heap management is a crucial, it is an aspect of the programming language. It is implemented here in the free storage. It might quickly to the exhausted. There is some way for returning allocated storage to be the free area. Here this memory allocated to hold a heap object, it can be released for later reuse. Here if the object is no longer accessible, if object is no longer accessible, on that longer accessible, on that time it is said to be a garbage. It is said to be a here garbage here. Here an object is garbage if two variable in the stack points recursively to the garbage points here. Here there are two main aspects here. First aspect is it is the recognition that allocated memory is garbage. Allocated memory is garbage here. And other one is the memory for new memory allocated request issued by the user. Request issued by the user here. Here in this garbage collection we are having who is required to notify the system that a given object. Here for example we take an object pointed by P, means in C++ we use the delete. In C++ we use the delete. Like that here. So we take another strategy to let the runtime system here take care the discovering garbage here. Here another means here we take, for example we take the object pointed by P in garbage. In C++ you would write delete. You would write delete here, and in Pascal you would write dispose of P. Here we, for example, in order to state the object pointed to P, object pointed by P here, in is it garbage, object pointed by P is garbage. In C++ we could write delete of P, and in Pascal we could write dispose of P. Dispose of P. Here there is no guarantee that only objects that become to define the garbage. Here the correct use of the delete entirely relies on the programmer's responsibility. Here you should programmer means it mark on the object as garbage here. Object as garbage here. Here next in this another strategy to the runtime system, it take care of the discovering garbage. Discovering garbage means of the suitable automatic garbage collection algorithm. It by suitable for the automatic garbage collection algorithm. It is suitable automatic garbage collection algorithm. Here another point is we have automatic garbage collection. It is vital for languages that make heavy use of dynamically generated variables. Dynamically generated variables like Lisp. Here in this automatic garbage collection for languages, it heavy use of dynamically generated variables like Lisp. Lisp programming language means list in processing. List in processing. List in process. Here in fact here garbage collection is invented for implementing the first Lisp systems. Here it is referenced by the pointers. In the it provides an the automatic garbage collector. Here this is usually treated in course of the data structures. This is usually treated as the course on the data structures. Up to this ma listen ma, up to this second unit is completed ma. This slide is contains the unit 1 assignment questions. First question is explain about software development process. Right ma, take questions. Are you writing? Hello, are you writing ma these questions? Take my first assignment, first unit assignment questions. In next class I will give unit 2 assignment questions. First unit assignment questions. First question, explain about software development process. Second question, explain about software design models language. Next third question, explain about computer architecture. Next fourth question, describe the programming language qualities. Next question, explain about language definition and language processing. Next, describe the following. First one, variables. Second one, routines. Next one, aliasing. And next one, overloading. These are the assignment questions. You have to write these questions and answers. Already I sent first unit material ma. Completed ma? Completed? Completed ma these assignment questions? All of you completed? Hello? హలో
మ్యామ్ చెప్పండి మ్యామ్.
కంప్లీట్ అయిపోయిందమ్మా అసైన్మెంట్ క్వశ్చన్స్ రాయడము. అసైన్మెంట్ క్వశ్చన్స్ రాయడం రాసుకున్నారా? వాటికి ఆన్సర్స్ రాయండి. మీకు మెటీరియల్ పంపించాను కదా. ఫస్ట్ యూనిట్ మెటీరియల్ పంపించాను కదమ్మా, అది అసైన్ రాయండి అమ్మా. నెక్స్ట్ వీక్ నాకు చూపించాలి, ఓకేనా?